Watson, 110. So I'm going to be covering part of Dr. Wong's material, like the first couple lectures. So some general anatomy of the brain. There are 4 important lobes: the frontal lobe, parietal lobe, occipital lobe, and the temporal lobe. This is just general anatomy. You probably won't get asked that on the exam, but it's important to know, especially for future parts in the course. Okay, psychophysics. Psychophysics is a scientific discipline that explores the relationship between physical stimuli and subjective responses. So this is really important, and a lot of Dr. Wong's material involves psychophysics and the psychometric functions. So psychometric functions are the fundamental data for psychophysics, and they relate the physical parameters to the subjective responses. And I'll show a couple of examples of psychometric functions on the following slides. But what's important to know is the x-axis plots the physical parameter of a stimulus, for example, stimulus intensity, and the y-axis plots the observer's response, which is like a probability or percent correct, something along those lines. 2 commonly used psychometric functions. The first one is an absolute psychometric function. These are very important for detection tasks. And the other type of psychometric function is a relative psychometric function. I'll discuss both and then some differences between them. So an example of a detection task is, let's say I put 1 square on a screen and I asked if you saw it or not, and I slowly made it darker or brighter along a varying scale of intensities of the square. And then I would plot here the percent of the squares that you saw at each stimulus intensity, and I would get a sigmoidal shape curve that looks about like that. So the goal of these detection tasks is to determine what stimulus intensity, at what stimulus intensity a subject is able to see or hear something or detect something. And the threshold for absolute detection tasks is 50%. That's also something that's important you want to keep in mind. And the x-axis units are relative stimulus magnitude. Yeah?
Just a quick question with your phrasing for the question, because that's how I think you determine absolute versus relative. If you're in that statement where you're saying if you see it or not, are you saying that you flash something and saying do you see it?
Yes, that's right.
You're forcing an answer. Wouldn't that be relative?
So for relative, you're usually trying to tell the difference between 2 things. So if I had like 2 squares side by side. So for a detection would be like, did you see it? And you say, yes, I saw it, or no, I didn't. And the reason why this goes from 0 to 100, which is for absolute, is because below a certain stimulus intensity, you'll never see it. Whereas for the case of the difference between 2 things, sometimes you might hear a difference and you might not, which is why it's 50 to 100. So that's another important thing. For absolute, it goes from 0 to 100%. And as we'll see on the next slide, for relative psychometric functions, it goes from 50 to 100%. So a relative psychometric function involves a discrimination task, which, as I said, is telling the difference between 2 things. So that's, for example, if I showed you 2 squares side by side, and I asked if the right square was darker than the left square. And 50% of the time you would get it right just by pure chance, by guessing, which is why in this case you have the y-axis go from 50 to 100, and the threshold is, instead of 50%, it's 75%. One key difference between the relative and the absolute is the label of the y-axis and the range. So I just talked about the range, but the label here is percent correct, whereas the label for the absolute is percent seen or percent heard. And that's important because here it's not like you're getting something correct. It's if you're able to detect, if you're able to see, or if you're able to hear it. So let's say you guys had to design a psychophysics experiment, and this would be specifically for a detection type experiment. So in order to generate physical stimuli, you would vary stimuli with small steps to a maximum value. So let's say you had to do a sound detection task. You would increment a stimulus, you would play a stimulus at, say, like 1 decibel, and every 1 decibel, you create a new stimulus. So from 0 to 100 in increments of 1 dB, right? So then you create a bunch of stimuli. So now what you do is you present the stimuli in random order, and this is very similar to the first homework that you guys did. So you present the stimuli in a random order, then the subject will respond if they saw or heard your stimulus. And you repeat that over multiple trials so that you're able to get a percentage for each stimulus magnitude. So if you did 10 different stimulus magnitudes, you'd play those in a random order, and then you would do that X number of times for different trials. And then over that, you would then determine the percentage that they saw or heard at each stimulus magnitude, which would be the number correct divided by the total number at a given stimulus magnitude. Then you would plot the psychometric function, which I'll show on the next slide, and then determine the threshold, as I talked about before. So this is a sample. So you'd have stimulus intensity, and in this case, let's say the units are dB, and percentage seen. The stimulus, since this is an absolute task, goes from, the y-axis goes from 0 to 100, and the threshold in this case would be 50%. And then you can identify, oh, so about 24 dB is their threshold for seeing something. So if you have, so Dr. Wong discussed this in class when he said, if I poke your finger with a dull probe versus with a really sharp needle, you're going to be a lot more sensitive for the sharp needle than for the dull probe. So if you're more sensitive, the psychometric function will be shifted to the left, and that makes sense because the threshold for the x-axis will have a lower stimulus intensity, which means that 50% of the time you'll be able to detect it at a much lower stimulus, which means you're a lot more sensitive. Whereas shifting the curve to the right would mean that you're a lot less sensitive because 50% of the time you'll get it right at a much higher stimulus value. So much larger, like depression of your skin or something like that. And let's say you had, if you were playing a tone at like 50 dB in a room that had background noise of 10 dB, that would shift your curve. To the right because there's an additional 10 dB background noise that you also have to take into account. So not just the tone that you have to hear, but you also have to hear the background noise in addition to it. So that is the empirical side of psychophysics, and then there's also signal detection theory. So here we have two distributions, and if we assume that noise is distributed like a normal or a Gaussian, and we have a constant signal at a specific value, you have your noise is a Gaussian, and your signal plus noise is also going to be a Gaussian distribution. So the mean of your noise distribution is just going to be shifted over to the right by the amount of the signal value. So let's say your noise has a mean of 10 dB background noise, and your signal has a constant value of 20 dB. The mean of your new signal plus noise distribution will be 30 dB. It'll be the sum of the noise plus the signal. And then you have this decision criteria, beta. So there are 4 possibilities for when you're trying to detect something. So let's say beta is your decision criteria. You can either correctly identify something as being the stimulus. You can incorrectly identifying the stimulus as being present, or correctly reject the stimulus, or have a false alarm. So the false alarm area would be the area under the noise curve that's greater than this beta value. So that's this area under the Gaussian. If the stimulus is present, then the correct detection is the area above beta for the signal plus noise curve. And the reason why is, so if there is no signal and there's just noise, but every time you have something that's above beta, you say that the stimulus is present, that means that if it's drawn from this noise distribution that's above beta, then you'll falsely say that the signal is there even though it's not there. So for everything less than beta, you say that there is no stimulus. That means that you will miss this portion of the signal plus noise distribution, and that you will correctly reject this larger portion of the noise distribution. I know that was a little confusing. Does anyone have any questions about that?
So the false alarm, is that the part that's only blue above beta? Or is it where the blue, is it also where the blue and the purple is?
So the false alarm is the area above beta under the noise distribution graph.
But is it also? Consider them separately?
Yeah, consider them separately.
Oh, okay.
So just the area under the noise is that false alarm. So yeah, April. So now I'm going to April.
Okay, so now that you've done the hits and false alarms, you know your probabilities of false alarms and hits. You can now use that to plot an ROC curve. So what the ROC curve tells you is how good your system is at detecting signal versus noise. So the worst case would be that straight line where your distributions completely overlap, so there's no discriminability, and your ROC curve is just a straight line in the like y equals x. But in general, your ROC curve is going to be above that, where you have some your distributions are separated, but there's still overlap, unless in the best case scenario where you have the ROC curve going straight up the y-axis and then straight across. So what you want from this is to know your probability of false alarms and your probabilities of hits, and use that to specify the points on this plot, and then draw an ROC curve through it. So that tells you how good your the signal detection is, and that's basically what you need to know from ROC curves. Just know how to plot points and draw. Oh, also, once you have a curve, that's like your system, and you can choose your beta threshold for how much false alarm and hits you want to get, and your beta value is going to just move you along that ROC curve that you have drawn. So a smaller beta value moves you to the left on your distributions graph, and so you're going to have more hits but also more false alarms, so you're going to be lower down on your ROC curve, and higher on your ROC curve, and the other way around for greater beta. Yeah. No. Okay. So.
I have a question on that.
Oh, yeah.
Would you mind going back to the slide though? Just one more slide. Okay, so what you're saying is that if you shift that beta to the right.
If you shift beta to the right, yeah.
The ROC curve is going to go closer to y equals x.
No, the ROC curve doesn't change. Doesn't change when you shift beta. ROC curve is just it's based on how far apart your distributions are, or the shape of your distributions. So it has no relation to your beta.
Okay.
So when you change your beta, you're just moving along the ROC curve.
Oh, okay.
Yeah.
I get what you mean now.
So, any other questions on that? Sorry. Okay. So one thing to touch on is the idea of a receptive field. And each neuron has its own individual receptive field. This specifies what it will respond to. So in your somatosensory system, it's your touch receptive field, the area where if the stimulus is inside that area, it will fire more. Just outside, it will not fire as much. And if it's completely out of the area, it won't be affected. And there's also the auditory receptive field, where each neuron has its own characteristic frequency, and so which you can tell from the tuning curve and the threshold. When you specify a threshold, your characteristic frequency is where the tuning curve is going to just touch that threshold. Any questions about that?
So I know for an auditory, it sort of goes down to like where the threshold, for like the tuning curve for your individual frequency. But for the somatosensory, would it go, since it's looking at increasing self-firing, would that threshold be a max instead of a min? I don't know if we have an example of that in class.
Yeah, I don't think we have an example, but just all you really need to know for now is that it will fire more in that region. So maybe if it was X and Y, but yeah, there was no specific example. Yeah?
What's the tuning curve?
The tuning curve, it's like that V-shaped curve.
It's still a receptive field.
Oh, okay.
Yeah, it's still a receptive field, but it's a different type of neuron. So so you characterize it differently.
Gotcha.
Yeah.
Okay, so that's specific to that type of V. Okay.
Yeah. Okay. So now spike trains, which you probably are used to by now, are the representation of all or none action potentials. So they're discrete. They're like you have a signal or you don't. And to quantify them, we use the mean firing rate as well as various types of histograms, including the post-stimulus histogram, the interspike interval histogram, and the period histogram. Yeah?
Can you just kind of go through the difference between histograms?
Yeah, they're coming up. So the post-stimulus time histogram, or post-stimulus histogram, is a plot of your firing rate versus your time after your stimulus. So t equals 0 is generally going to be your stimulus time. And then you're going to, from what you see on dot raster, which is just a pile up of spike trains, you're going to see the spike train signals begin like quite soon after your stimulus. So what you want here is to count up the number of spikes in time bins after your stimulus. So say you want bins of 20 milliseconds, and you're just going to count the number of spikes between 0 and 19, 20 and 39, and so on. So you tally those up, and then you plot the histogram, which tells you when that neuron responds compared to the stimulus time. Yeah?
What's on the y-axis of the top?
Oh, the top is just the number, like the trial number, basically.
Oh, okay.
Yeah, it's like a stack of spike trains.
So when you're making that graph, would you just like average out the trial?
So when you make the graph, you count up your spikes, and you divide those. You divide the spikes by your bin width, since that's your time interval. So you're essentially getting a mean firing rate for each bin.
Are you getting the mean firing? I thought this was not anything to do with mean firing rate.
Well, it's not, but you're getting a firing rate.
Okay.
But it's kind of the mean for that like time bin.
Okay.
Yeah.
So you do that for each trial and you divide by the number of trials?
So you total this up over all your trials. So if your time bins are 20 milliseconds, then you divide your counts by 20 milliseconds. Any other questions? Okay. Then you also need to know the interspike interval histogram, which now instead of your x-axis being time after your stimulus, it's the length of your interval between your spikes. So this time, instead of simply counting when your spikes are occurring, you need to first calculate the length between each spike. So if you have a spike at 11 and a spike at 20, you're going to have an ISI of 9. And so you're going to calculate all of those interspike intervals and then tally those up and plot them. So this time you have number of spikes on your y-axis and your interspike interval, which is in terms of time, on your x-axis. Yeah?
So on the test, would they give us a spike train and then they would ask us to like make this histogram?
Yes. Any other questions?
Just to clarify a little bit, instead of saying like number of spikes, is that like the number of periods that are of this certain length? Are those good equivalent statements?
Yeah, so I mean, if you have a spike at 10 and spike, yeah.
Because I think where I'm a little bit confused with this one is the y label is number of spikes and the x label as IX.
Right. So.
I also just might be thinking about this.
No, it's fine. Yeah, it seems like they were being off by one error. The number of total spikes.
I think you're thinking right. You could think of it as the number of spikes or sets of spikes that take on that interval. So
Yeah.
you could think number of instances and number of occurrences and things like that.
The number of things that you probably do, like the number of things.
Yeah.
Yeah. Any more questions on ISI? Okay. So the last one is the period histogram, which is very similar to the post-stimulus histogram, but this time, instead of t equals 0 being your stimulus, your t equals 0 is some point in your stimulus period that you choose. So your stimulus here is periodic. So you choose arbitrarily a point within that period, and then you take several of periods and count up your spikes in terms of bins after that arbitrary point you chose. That was probably unclear.
So is it basically you have like that, sinusoidal. You take a chunk, let's say you take 3 of those. And you break each chunk up by 3 peaks of your stimulus, and you look at in those individual ones the spikes.
So you're looking at each period.
But in the lecture, it takes you don't just do periods. You take like 6.
Right. So there they were taking 6, and then they were looking at each one of those 6.
But their period histogram had 3 spikes. It was at each peak of the, because they broke it up not by 6.
Oh, okay. Yeah, you can do that too. Yeah.
You basically just break it up however you want, and you just use only that time bin. And you just
Yep.
look at every single trial.
Mm-hmm.
For what you're okay.
Yeah, so if you have 6 periods, then you can do like 6 periods and the next 6 periods and the next 6 periods.
Okay, cool.
And count it out. Yep.
So theoretically, if you had the periodic stimulus,
Mm-hmm.
you should get the same histogram no matter where, like what point you chose.
Yeah. Oh, yes, the same shape.
Yeah.
Yeah. Any more questions about period histogram?
I'm just kind of lost on this one, to be honest.
Okay.
Is there like a resource I could go
Hmm?
to like get a more like fundamental understanding of everything that's going on in this one? Because I feel like it's like more
Oh,
what needs to be gone over in the review session.
yeah. So, where is the marker? There's the marker.
Yeah, I was really asking like
Oh.
what lecture it's from. Oh, there's a Wednesday.
4.
Lecture 4?
Lecture 4. Okay. Are we good? Okay. Oh, no summary. Sorry. Yeah, so, okay. Dr. Wang, what you should probably focus on is your signal detection theory and your spike train quantitative analysis. Yep.
So question, the parts talking about quantifying phase locking and quantifying randomness,
Mm-hmm.
ignore them?
Quantifying phase locking, quantifying
With the
randomness.
vector strength and then the thing that I was going to
Oh, yeah.
just ignore all that?
Yeah.
Oh, great. Half of this page is useless.
There's like 3 graphs? I thought there were 4.
Mean firing rate.
Oh, the other one was mean firing rate. So you have so the 4 ways to quantify your spike train is your mean firing rate, which is simply totaling all your spikes and dividing by your, like, the duration that you totaled them over. So if you have 5 trials and each are 100 milliseconds, then you're going to divide it by 500 in the end. You total the number of spikes and you divide it by 500. So that's the 4th thing, and then you have your, post-stimulus, ISI, and period.
For the signal detection, like types of questions for that would be sort of talking about your hits. Like, would they're not going to have us, or do you expect us to have to like, do the actual integral of the PDFs for the Gaussian? Because that Gaussian distribution has a terrible PDF. Okay, so just more of the conceptual parts of it?
Yeah, you have to know the idea of doing an integral, but you don't have to actually do any hard integrals.
Okay.
Yeah.
Okay.
Any more questions? Okay.
Okay, so these are all the questions that you don't have all the answers to already from the old exams. So all those secret rubrics that you have hidden away aren't going to help you at all for this part. Sorry, but that's okay because now you can actually, study and try to get it. So I'm going to go over the first 2 lectures from Dr. Sarma, and does work. Okay, and she started out by talking talking about spikes being the language of the brain. This is how the brain communicates. You measure the spiking activity of a neuron, and you can you call it a spike essentially, and it gives you information about what's going on in the brain supposedly. So the idea is you can use these spikes to design experiments, create models, learn something about the body, about the human body, or animal for that matter. So it's nice to think of her stuff if you zoom out a little bit, because there's a lot of complicated math and statistics and things like that. So it can be helpful to take a step back and think about what's actually going on. And so what we do as engineers is we design some sort of experiment, because then we're going to want to collect some data to evaluate some system. Okay, and when you collect a bunch of data, particularly spiking data from humans or animals, you want to find a way to describe that activity. And so you can use a lot of modeling techniques to try to describe these spiking activity. So for instance, like Poisson distribution, Dr. Wong talked about it, Dr. Sarma talked about it. It's a good way to, get a rough estimate about what's going on. So you propose these models, and then you have to say, okay, well, how does this model fit with all this data we collected? And is it useful? Does it tell us anything we want to know? And there's some techniques for evaluating the model quality, which is what she talked about later on in her lectures. So you evaluate your model, you look to see how good it is, and you make some prediction about what's going on in either the human or the animal that you're studying. So it's important, because what happens is you start to evaluate your model quality, and then you go back to propose new models, and you use these predictions you make from your good models to make new scientific discovery. So it's a continuous cycle. So it's important to, I guess from our point of view, understand what's going on and what the different components of each of these things are, and how it kind of plays into what Dr. Sarma has been teaching. So some of the things, like for instance, the point process model you can use to fit your data, and she talked about time rescaling theory, a KS plot to really evaluate how good your model actually is. Okay, so one of the first examples she gave, and this is what y'all did in homework 3, which I'm sure a lot of y'all are upset that you didn't get all the points you wanted to, but it's hot shit, you can deal with it. The rubric will get posted later, but don't worry too much about it. It's like 1%, 1.5% of your entire grade, so just relax. It's okay if you didn't get 100. But what's going on is you have a rat that's running around, and you are measuring activity from a particular neuron in that rat's brain, just one neuron. And so you can see that it's active in certain positions in space, so that tells you something about, oh, well, maybe this particular part of the brain is communicating with the rat, and it's only responding when he's in a certain position in space. So, that's something that would be useful that we could generate a model for, which is what you did in homework 3. And to do that, you can mess with this conditional intensity function, that lambda hat, lambda delta t. It's essentially an equation that you can use to describe your data. Okay, so one of the common ways to model neuron activity is with a Poisson process. I know you all know that this isn't a perfect representation, because you have things like a refractory period that causes a delay in spiking activity, so to speak. You can't have two spikes occur within an instant of each other. You have to have some refractory period, so that you can incorporate that into other distributions like a modified Poisson process. But it's important to understand how you can take a particular distribution like a Poisson process and calculate the probability of seeing a particular event by making the assumption that it's of this distribution type. So if she asks you a question, write the probability of seeing a spike in this time bin, you're going to want to use this equation because it's describing the probability of a Poisson distribution. Yes?
Will we be given any equations for this part?
I don't know. You're not going to need to know any equation for lambda, right? Because lambda is dependent on your data. Right? You're proposing the model for lambda, but it would be helpful to know, you know, something like this. How do you write the probability of a Poisson distribution? Because well, there's a difference between continuous and point processes, which we can come back to if you have questions, but she gave this example, right? Like how are you going to write this probability? So knowing how to write that probability, she's not going to give you the equation for it because you're going to need to put 2 and 2 together and say, well, I'm going to assume it's a Poisson distribution and here's the probability equation for a Poisson distribution. You had a question in the back? Same question, same answer. Okay. So this is a good exercise. I would recommend you doing it. And we can step through it, and we did this in section 2. It's what's the probability of seeing one spike here and nothing in the time bins 1 through 3. And so what you're going to do is you write the probability for the probability of seeing one spike in each bin, and you multiply it together, right? Because you remember the probability of flipping 2 heads in a row is 50% times 50%. So that's a 25% chance that you're going to flip 2 heads in a row if you have a coin. The same idea here, where every time bin you're going to need to multiply the probabilities by each other. And this comes into play in a little bit down the road when you start talking about likelihood functions and things like that. So going back to that equation, you can write this out. Does anybody remember that equation?
Lambda delta t quantity to the whatever n.
Let's see. Lambda k delta t.
Together with n power.
Okay.
And then all over n factorial, but also e to the lambda t.
Could you check it? There might be a negative in front.
Oh, negative, yeah.
Yeah.
And then I think that's the yen or no? No.
No. Oh well. Okay. So this is a probability for a Poisson distribution, and if we're going to assume that this spike train follows a Poisson distribution, we can use this for every time bin. So what's the probability of seeing no spikes in bin 1? Well, what does n become? What's the 0 factorial? Okay, good, because you can't divide by 0. And then what happens when you make this exponent 0? Yeah, this becomes 1 if that is 0. So all you have left is this term, right? And you can do that for every bin until you hit bin 4, which is where you say, well, now let's pretend n equals 1. What's the probability of seeing a spike here? And that's why you have this term right there. Make sense? So the question is, well, what happens if n is like 1,000, right? It's kind of unlikely, but could you write an equation to represent that probability for any given spike bin, right? The only thing that's going to change is you have now 1,000 factorial in your denominator, which is basically going to make the whole thing 0, but theoretically you could do it, right? Makes sense? Okay. And then you can simplify, so, which is always nice. But on the exam, I don't think you would have to worry too much about simplifying, other than you know, your basic simplification to get something that could reasonably be argued as the final solution. Yeah.
Assuming history doesn't matter
Here, yeah, history doesn't matter. That's a good point, because for a non-Poisson case, you say, okay, well, let's say history now does matter. Let's say the probability of seeing something in spike or in bin 1 is the same, but now the probability of seeing something in spike 2 is completely dependent on what happened previously. So you have what's called this conditional probability. And then the same thing for bin 3. What you see in bin 3 is going to depend on what you saw in bins 1 and 2. So that's called a conditional probability, and This is where Bayes' theorem comes in. And she mentioned it very briefly in class and wrote it up on the board, but essentially it's a theorem that describes how you can write the probability of some event given that another event has happened. So you would read this in words, or if you're going to tell your grandma what this meant, you would say the probability of seeing A given that B has happened is equal to the probability that B has happened given A times the probability of A by itself divided by the probability of B. And you can, they write it this way, but really what it looks like if you multiply it out or simplify a little bit, it's your conditional probability function. And if y'all have had any statistics or probability classes, you've probably seen this before. But these two are equivalent. The probability of seeing something dependent on the other times the probability of that other thing is equal to the reverse of that. So it's not, I don't think you're going to need to know this kind of theory or these kinds of equations, but it's something that's important to keep in mind and be aware of, that you can have things that, you can't have equations where you write conditional probabilities when you start talking about history. Okay, all makes sense so far? So this leads us to that conditional intensity function lambda, which is what you were supposed to come up with for homework 3, and then homework 4, in case you haven't figured it out, you can use the old lambda models from homework 3. Right, everybody realize that? She's giving you a lot of the code. You don't have to do a lot of the stuff on your own. But this, you can write it to take into account things like history or position, like you saw in the homework, right? So this is a way to generalize the model that you've created by saying, okay, well, we see all this activity. How can we write an equation that represents that, you know, says, oh, this is what we think is going on, and this equation for lambda, this conditional intensity function, seems to capture that type of information. Okay, so this is a little icky, but it's useful to know because this is where some of the simplifications come in. The idea is you can take the probability for a Poisson distribution and you can shrink your time bin so small that the likelihood of seeing more than one spike is basically 0. Okay, and you'll realize that, I'm sorry?
I didn't know it was a 0. I thought that was an
Oh, this is a higher order term that is basically 0. So what's happening is if you can, if you remember from calculus 1 or whatever, pre-cal, you can expand an exponent as, so e to the x can be expanded, or e to the negative x can be expanded as 1 minus x, I think, plus x squared over 2 factorial or something like that. You can expand it out. And the idea is, well, if you make this x small enough, as soon as you get to these higher order terms, they're basically 0. They don't have a huge impact on your outcome. So that's why you can write it this way, this O of t, meaning that these higher order terms for delta t are so insignificant that they sort of drop out. So it's good to be aware of this, but keep in mind this isn't always the case, right? Maybe your delta t is so big that you could potentially have more than one spike, in which case these assumptions may not hold true. Okay. So all this leads into likelihood and maximum likelihood estimations, which I'm not going to get into because Nisu has a nice presentation prepared for y'all just on this. So I won't say much other than it kind of follows the same idea of where when you want to calculate the probability of, say, seeing a spike train or seeing a specific spiking events in a particular bin, you multiply your probabilities together. Okay, that's what this capital pi stands for. You're multiplying each one of those probabilities by the next one. So more on that to follow. Okay, this time rescaling, this is more along the lines of evaluating the quality of your model, which I'm sure since y'all are all smart and here for the review, it means you've already done your homework probably and have already done this. But it's a way of testing how good your model is. It's something you need to do in order to generate what's called the KS plot. So if you remember, you can write the probability for seeing a single spike in a particular time bin. And the idea is, well, you make a change of variables, because if you make this change in variable, your probability then becomes an exponential distribution of rate 1. So the idea is, well, you do this time rescaling with your conditional intensity function, lambda, and then you're going to test it after you've rescaled it to see if all of these variables that you've now changed to are independent and identically distributed. Because there is a theorem, the time rescaling theorem, that said if you make this transformation, everything should be independent and identically distributed with a distribution of exponential rate 1, okay? So that's why a KS plot works. So because of the time rescaling, you can do the KS plot to see how good your model actually is. And what you're plotting is the cumulative distribution function of a normal exponential distribution of rate 1. And you're comparing it to what's called your empirical cumulative distribution function, which is the data that you've extracted from your model. And if everything is perfect, then it should match up on this line, this 45-degree line, which is an exact fit. So one thing to keep in mind is when you're doing your homework and you make a KS plot, be sure to describe what all of your lines mean, right? Because you can't just have this 45-degree line sitting in the middle of your plot and not tell anybody what it is. So expect points to be taken off if you don't have it. Yeah.
So what is the 45-degree line?
So good question. This is, the 45-degree line represents an exact fit. So this, if you had a plot and it was y equals x, what would it look like? It would look like that, right? It'd be it's just a straight line, 45-degree line.
If you were to say ideal fit, does that work too?
Yeah. Yeah, that should be okay. As long as you point out that that 45-degree line means something. Yeah.
So
Yeah. 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 Mm-hmm.
So when we're in class, she like showed us how to transform disease. Would we have to like be able to do that on the kit?
I don't think so. No, she's a sweetheart, really. So she's not going to ask you anything too crazy, but I don't think she's going to ask you anything super theoretical like that. Yeah.
Do we only need to know what this is and not how to actually compute it?
So if you notice, like in the MATLAB has a bunch of built-in functions that are doing these model fitting and this maximum likelihood estimation for you. I would say you need to know how to find maximum likelihood, how to do a maximum likelihood estimation. Why?
More on like the exam, like on paper.
Yeah, on paper, no, because it's there's some hokey pokey theory behind it, and it's kind of outside the scope of this class, but it's important to understand why it works, what it does, why it's useful in the big picture, to help evaluate your model. But calculating it by hand, I don't think so. But if you were to calculate by hand, you could figure out the KS distance, which is the maximum distance between your perfect fit and the largest deviation in your model. So KS distance is one number, and it's going to be the furthest point away. Does that make sense? So you could calculate that if they gave it to you.
Is there a specific threshold number that we can say that, oh, we have a nice fit, except from the visual?
I don't know. Not that I'm aware of. Nisu might know. I think it's probably application dependent, and they probably look at things like relative improvement, things like that.
You get one number. Let's say if you try 3 models, for sure you're gonna find the minimum value out of this. But finally, none of them is good.
Yeah, but one's better than the other, right? Yeah. See, that's how you get published. You compare it to things that are worse.
Yeah, I know.
So just to know, like the 2 terms in the equation, which one?
Which one's which? It won't matter. I think this is if it's perfect, because you're taking the absolute value. It won't matter. You just take the difference between that point and that point.
Is it always vertical? Or it's like distance as in like, does that look like it's like looking straight vertical at distance, or is it more closest to?
Oh, that's a good question. You know, I'm not sure. I imagine you could do either. You might be able to take the further the KS distance in.
Vertical then, because you're trying to find the distance between corresponding points.
Ta-da. No. Smart. Y'all agree with that? Yeah, okay. Thank you for that. You saved my butt. Whew. Okay, and this is what a KS plot looks like. You'll notice here we did a very poor job at labeling, so sorry. Yeah, points off. 50%. And this is comparing the cumulative distribution function, so you can kind of see how it's transformed into that, yeah.
So I see there's like the 45-degree line. What are those dotted lines?
Even better question. These are your 95% confidence interval lines. So maybe you could use that as a metric of saying how good your model is. You could say, well, it doesn't necessarily exceed this confidence interval. So maybe that's a good metric for saying how good it is. If you have some predefined threshold of your confidence interval, you know, maybe 95%. But if you exceed it, yeah. So that's again where you know, make the threshold what you want so you look good. Yeah.
Are these colors reversed as in like the empirical CDF is supposed to be what the green line is the right one?
Oh, good point. So the reason being the color that MATLAB defaults to when it plots is blue. So if you have one curve, it's always going to be blue. So not necessarily. This is plotting the blue versus the green to generate the new blue curve.
Right, but just to make sure, like the empirical CDF, that would be like the exact fit.
Yes.
Okay.
No, I'm sorry.
No.
I'm sorry. The model CDF is the exponential distribution rate one that you want. That's the perfect one.
That's the perfect one.
Yeah. So this green would be.
So is that legend? I might be just misinterpreting the term empirical, which is kind of depressing, but to me, it's like the model CDF would not be the one that.
Yeah, I think it's confusing because when you hear model, you think back to the lambda equation that you've been writing the whole time. So here, think of this as like your role model. You know, this is like Kim Kardashian CDF, and that's like Kanye West CDF. Okay. Well, we all got to do something. Okay. Yeah.
X and Y axis labels in the graph on the right.
I'm sorry, say that again?
I don't understand the X and Y axis.
So this is the perfect one, the exponential rate 1 distribution, cumulative distribution function. And this is your empirical cumulative distribution function. So basically you could think of the green line as your x axis, and then the blue line is your y axis. So it's a different way of visualizing this plot. And I think that's it. Yeah. It won't go any further, so I'm all done. Are there any, yeah?
What do we have to know with time rescaling for the second test? Like, do you have maybe any conceptual questions?
I don't know. If I had to guess, I would say knowing what it does and why you need it.
Isn't it, so you just need it so you get a identical and the IID,
Yep.
which is identical and independent distributed, and why do you need the rate 1?
It's the way the theory works out. You can dig up some old paper if you'd like, but there's actually some notes on it. I think on Blackboard that there's a paper written on time rescaling and this theorem that you can read if you're interested in, but it won't be required knowledge for the exam.
So basically you use it so that you can do the K statistic.
Yeah.
And that's the two things, IID and...
Yeah.
Okay.
Yeah. Yep. Clear as mud, huh? Alrighty. Good enough.
Still flashing.
Okay, cool. Okay, so I'm going to cover the last 3 lectures that Dr. Sarma had. So this is all the general linear models, what the exponential family is, what a canonical link function is, and then I'll cover one of the case examples that she presented, which was the retinal example. And then you should have enough knowledge to kind of go back and look at the Parkinson's example. But so just as an outline, I'll cover maximum likelihood estimations, right? I'll give you an example that you maybe haven't seen so far. So after this, you would have seen 3 examples. She covered binomial, the TAs covered Gaussian, and then I'll cover exponential. So those are 3 examples of maximum likelihood. So you guys should be really good about doing the kind of the mechanistic process of MLE. And then I'll cover some of the basics of GLMs and how they kind of go, they extend beyond Poisson and point processes to cover more complicated behavior. We'll cover the exponential family, canonical link functions, and then the example, like I said. So basically, the purpose of maximum likelihood estimation is to find the parameters that best describe your data, right? You collect a bunch of data and you want to know what distribution they come from. You use maximum likelihood estimation to get that value. Because if you're looking at a system, you don't know all the details of it. You're just kind of collecting macroscopic data. You're trying to find what parameters best fit it. So by parameters, I mean a few of the examples I listed here. So for Bernoulli, once you have the probability of getting a yes, you have the entire distribution, right? For a Gaussian, once you have the mean and the standard deviation, you have the entire distribution. And finally, for Poisson, like you saw in Poisson process, once you have lambda, you have the entire thing. So essentially, the entire behavior of the neuron is encoded in whatever parameter you choose to classify it as. There are 4 major steps to doing an MLE. So the first is you want to write down the PDF, right, the probability density function. And you should kind of know these 4 just because they've showed up in previous lectures and in previous examples, right? So you guys all know the binomial. You have a bunch of coin flips. What is the probability of getting that coin flip? You guys know Poisson from what Luke talked about. And then exponential, after time rescaling, this is the distribution with just lambda equal to 1. And then Gaussian, you all should also know. So these are 4, pretty good PDFs just to have in the back of your mind. And so for our example, what we're going to say is that let's say you collect a bunch of data, x1 through xn, right? And you're going to say that they are independent and identically distributed. That's what IID means, independent and identically distributed through an exponential with lambda. So I put the PDF right here of an exponential with lambda. And we want to know, based on the data that we get, what is the most likely lambda value that can classify this system, right? So like I said, write down the likelihood. And the likelihood, as Luke mentioned, is just the product of the different PDFs, right? So you get a bunch of values, you multiply the probability of getting each of the values. That's your likelihood. So for our example, here it is. This is the PDF for getting xi. And this is the entire likelihood. And so here I just simplified. Basically, I took this out. Because you're multiplying n of these, it's lambda to the n. And then this product can go into the sum of the exponent. Yeah?
Is this specifically to our neuron case? Because I'm curious because... never mind, that was a wrong question. Not there yet.
Okay, well, it can be, right? You can think of x1 through xn as just the number of spikes in different bins, and you're trying to fit an exponential with a lambda parameter to it. So usually, after you write down likelihood, you take the log of it, and the reason why you take the log of it is usually all the distributions that you deal with, they have a bunch of e's, they have a bunch of exponents. Logs just kind of bring them down, make them easier to work with. And the reason why that works is log is a monotonically increasing function, right? It keeps going up. And so when you take a function of something that's monotonically increasing, the maximum of that is at the exact same place. It doesn't shift, right? And that's essentially what we care about. What is the most likely, the maximum likelihood parameter? So we'll just take the log of it. And that's denoted as little l big L was a likelihood, little l is the log likelihood. So I did it over here, but it's pretty easy. You just take the log of this, you separate out these two terms and bring the exponents down. After you take the log of it, you take the derivative with respect to each of the parameters, right? So in the homework, you guys are dealing with betas and beta naughts and beta 2 and beta 1. So you take the derivative of your likelihood with respect to each of the beta values. And so the example over here is right here. And then finally, you set the derivative equal to 0. That's what maximum is. And there should be one step after this where you take the second derivative, say that it's concave down and that it's actual maximum. For most purposes, we can just ignore that and just take the derivative and set it to 0. So in our example with the x1 through xn, that was exponential with rate lambda. Here is the MLE estimate. And most of these are going to be fairly, yeah?
So then on the example, you won't have to do the second derivative test and check it out? Or?
You don't need to, yeah. And I'll get into why later on. But for the exam, if you're given an MLE problem, take the derivative, set it to 0, find whatever your MLE estimate is. And most of these are fairly intuitive, right? So the Gaussian example that you guys saw, the MLE was the mean. And that's what you would expect, right? If you're given a bunch of data that you think is Gaussian, your best estimate for that would be the mean. So these are fairly intuitive, but this is just kind of a more mathematical background for it. So what do GLMs allow us to do? They allow us to go beyond Poisson and point processes. In a Poisson process, you saw that the number of events in a certain time bin is Poisson distributed. But now with GLMs, we can fit Gaussians, betas, Bernoullis, whatever distribution that you want to fit. And it just allows for more flexibility. Luke mentioned one of the drawbacks of Poisson was refractory periods. You can use a gamma if you want and get that refractory period. So they allow for more complicated behavior to be modeled. And they allow generalization to something called the exponential family. And so what that means is most of the distributions that you guys have probably seen are part of this like kind of super family of distributions. And the exponential family is any distribution, any PDF that can be written in this form, right? So this is kind of there's a lot happening. But basically, if you can break it down into the exponent of a function of the data, a function of your parameters, plus a function of data, plus a function of parameters, then it's part of the exponential distribution. So some examples are Gaussian, binomial, all the ones listed here. And this C function has a special name. It's called the canonical link function. And it basically lets you fit a certain model to that distribution. And I'll get into that later. But basically, she went over a few examples of how you turn Poisson into this form or how you turn a binomial into this form. And they all end up with this structure right here. So here's an example of a Bernoulli. So Bernoulli, you just have one coin flip. Is it yes? Is it no? What is the probability? So the PDF of that one is right here. And a lot of these rely on the e to the log x is x trick. That's what's happening in this line over here. And then as you can see, function of the data, parameters, and then parameters, right? The one that was supposed to be your data is a 0. And so, like I said, the one that multiplies the function of the parameters, the function of the data is called your canonical link function. So for a Bernoulli, your canonical link function is log p over 1 minus p. For Poisson, it's log lambda. For a Gaussian, it's just mu. Are there any questions so far? No? Okay, cool.
Wait, can you repeat what it was for Poisson distribution?
Poisson, so it's log lambda. And it'd be good if you went through the example and you can just see that come out of the manipulations that you do to get it to this form. Instead of a p over 1 minus p, you'd see a lambda over here. So given any PDF, you can do these tricks. And if you can, then it's part of the exponential distribution. And then you should be able to find whatever the canonical link function is. So the way GLMs work is the input is always a covariate, right? So you kind of heard this term a lot. A covariate is basically anything that you think affects the thing that you want to study, right? So a toy example, Let's say you find, you're trying to find the happiness level of a bunch of people, right? And you ask them, how happy are you? And you have a scale of 1 through 100, right? That can be your Y. Your covariates would be, what is their GPA? How much sleep did they get? Things like that. What is their income level? Because you think those affect their happiness. So covariates are just things that you think are relevant to explaining the data. And the way GLMs work is you set the canonical link function to a linear function of your covariates, right? That's where generalized linear model comes in. That's where it comes in from. You set it to a linear function of your covariates. And each of these beta values are your weights. So they basically tell you how much that covariate affects the final output, right? So if you have a super, super strong beta, then you know that that covariate has a lot of effect on the final output. Yeah, and this is a constant term, so when you're dealing with neurons, you can think of that as just base level firing. You're not really putting in anything, it fires because neurons are stochastic. So that's generally how GLMs work. So as an example, for Poisson distributions, you would put in log lambda here, and that's kind of what you've been doing in the homework because we're working with Poisson distributions. But if she had told you, let's say it's Gaussian, you would put in whatever the canonical link function for a Gaussian is over here. Okay? So yeah, like I said, you set it equal to a linear function in the covariates. Then once you have that, you can get your likelihood, right? Because then you have the PDF of it. You just multiply it for all of your data. You can use MLE in theory to get the distributions. And then you just invert the canonical link function to get the parameters, right? To get this, you have to invert this function. And this is essentially what you care about. Because like I mentioned, once you have the parameters to a distribution, you have the entire thing. So yeah, in theory, you should be able to use MLE to find any, to find the best fits for any models. Turns out a lot of the times when you're dealing with these type of things, there's no way to do it analytically, and so that's what GLM fit does. It does this, it does an optimization stuff, and it calculates this MLE to get you your final beta values. So here's the case study that she kind of touched on, and I'll just run through it again because it's very instructive. So basically, the experiment was you have a bunch of retinal cells in a petri dish, and you just shine constant light at them for a long time, and you collect the recording of the spikes, right? And as you saw in class, you know, when you give a neuron a constant stimulus, eventually it drops off, right? That's what happens here. But there's some other behavior of the neuron that a regular fit may not account for, right? So one of them is a refractory period right here. And then also you have a huge jump immediately after the stimulus begins. And then you also have some long-term history dependence, right? So when you try to fit one of the regular ones like exponential, gamma, or whatever, they don't really, they're not even close to what the actual fit should be. So you need something a little bit more complicated, and that's where GLMs come in. So basically, this is the model that she decided that she wanted to fit to the retinal cells, right? So from the log lambda, you should be able to tell that it's a Poisson distribution, a Poisson model that she's using. And here are the covariates, right? So the covariates over here are the number of spikes that are I bins before wherever you are right now, right? And this goes all the way up to the order. So the order is just how many spike bins do I care about, right? So the order can go from 1 to however many data you have. And for each order, there's a different beta value. So as you increase the order, you get more and more parameters. And so if your order is as big as your data, you're going to fit any model because you have as many parameters as you have data. The trick is trying to get a lower number that still gives you the best fit.
Sorry.
Yeah.
It's I equal to 1, right?
Yes, sorry, yeah. So you don't count the bin that you're in right now because that's what your data is.
I've already put that before the beta 0, but when we say we have 3 parameters, it's order 3, it's not order 2, right?
Sorry?
When we have 3 parameters, it's third order.
Yes.
I mean, the first one will not have a covariate, but the other 2 will have, so, but it's a third order.
So if you have 3 parameters, right, then it's a second order. Because your first parameter is here. right? You still need to fit this. It's still important. And if you add more and more here, this is going to change. They're not independent. Yeah. Are there any other questions on this? Cool. Okay. So, you know, you can fit a bunch of these different orders all the way up to 100, right? And what she found was that 1 is super shitty. But then when you go to 14, it gets really good. As Luke was saying, it's in your 95% confidence intervals. And then, of course, 50 is there also, because if you just keep adding more parameters, you can explain more and more. But it's not that much better. And so 14 is good enough for the trade-off between a better fit and the number of parameters. And this is where the AIC comes in, right? So you guys have been using AIC to evaluate some of your models in the homework. And AIC basically compares how much better you get in your fit versus more and more parameters you're adding. So you want to minimize AIC. So you want essentially the most bang for your buck per parameter. So yeah, just to go over kind of whirlwind over GLMs. First, I talked about computing an MLE. So you write down the likelihood, take the log, take a derivative, set it to 0. Then we know that GLMs extend Poisson and point processes. So normally, you know, when you deal with Poisson distributions, the number of events in a bin is Poisson distributed. Now you can have beta, you can have Gaussian, you can have any distribution that you want to fit. And then the way you fit it, by fit, I mean you take your canonical link function, right, whatever it is for that distribution, you set it equal to a linear function of your covariates, right, what you think affects the data, and then you use an MLE to find the maximum parameters. And then finally, you invert the canonical link function to get whatever parameter you care about. So it could be lambda, it could be mu, whatever. Yeah. Any questions?
How do you determine which canonical link function you should use? Like in real life, I mean, like. So. Because the whole idea is that your model, the data doesn't fit any one parameter, right? It doesn't fit Poisson, it doesn't fit normal.
Right.
So then how would you choose? What makes you want to choose?
Yeah, so that's when you make an assumption, because neurons are not going to be like exact, right? That's where you say, I think a Poisson is good enough, but I'm going to add covariates to kind of explain some of that like nasty behavior that we can't really get. Yeah.
So we kept talking about Poisson not being history dependent, and you know that, but you just mentioned the covariate thing because we talked about in class that you're still using Poisson, basically use Poisson for most of it, but we just added the covariates time history. But that is still. That
makes it not independent. Is that what you're asking?
Right. Still using point process.
Right. And so the trick is it's still independent given the history. So that's kind of like a weird thing, right? So it's conditionally independent, right? If you're given the history, you don't need anything else to calculate the probability in the next spike interval.
And we've always just in class we only really considered just the last spike or the last bit.
Yeah, but I mean,
can't do more, yeah.
Right? It would just be kind of going back more and more.
And then another question with the MLE sort of thing. So writing down the likelihood, that would just be going like for our, let's say, our same lambda sort of process, or you still have that pi-looking summation product, and then you take it in respect to each parameter. So like for the linear model from homework, so you take it in respect to beta 0 to beta 1 and then beta.
The MLE, yeah.
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 So you find values for what then? Beta 0, beta.
Right. And then that's when you plug them into your canonical link function and you invert it to get your parameter.
Okay.
Right, so in the homework when you find all your betas, you take the exponential of it because that's the inverse of the log lambda.
Can you say that one more time? How you maximum likely you set the beta to 0 or set it to 0?
Yeah, sorry. Yeah, so what you do is you basically plug in that, like that beta naught equals the sum beta 1 x1, right? You plug that in here, right? And that is your likelihood. So you maximize that over all of your betas, right? This is essentially your likelihood if you just do this for each of the data. Does that make sense?
Okay, so then once you have your estimated maximum likelihood for your parameters,
Mm-hmm.
you just do inverse of your canonical?
Yep. And so that's exactly what you guys did when you took the exponential, right? That's the inverse of log. That's essentially what you did, yeah. Okay, any other questions? Yeah.
Still just kind of confused about the canonical.
Okay.
Can you talk about, so how do we figure it out from the PDF? We take the
From the PDF, exactly. So what you do is from the PDF, you want to try to put it into this form, right? And so this is a pretty specific form, right? It can only be a function of the data times a function of the parameters plus a function of the data plus a function of the parameters. And so not every distribution can go into this form, but for the ones that can, we can use GLMs to find the best fit. Yeah.
Assume that any distribution would be given on the exam could be put into this form.
I'm sorry?
Can we assume that any distribution that would be given on the exam would be put into this form?
Yeah, so like I said, most distributions that you do work with, right, can be put into that form. Yeah. Yeah.
Can you just repeat your intuitive definition of AIC? You said like compares how much better?
Yeah, so actually I'll write down the mathematical definition and then I'll break it down. So I'll write it here. I apologize in advance for my handwriting. But basically it's -2, right, times the likelihood of your parameters plus 2 times the number of parameters. Okay? And, sorry, this should be log. Okay. So it's -2 times the log of your likelihood plus 2 times the number of parameters that you have.
Isn't that just a deviance then?
Sorry?
Isn't there something that's just a deviance in here?
Yeah, so in the homework what she did was she added a constant offset, and then that term plus this term becomes the deviance. Because you only really use AIC to compare two models, so a constant offset is going to raise everything by the same amount. But that's your AIC, right? So if you minimize your AIC, essentially you're trying to maximize your likelihood, right? Or I'll say it the opposite. If you maximize your likelihood, if you take the -2 log of that, you're minimizing that function. And then you basically penalize for the number of parameters that you have. And so as P goes up, your AIC goes more and more up, and you're more likely to kind of reject that model. Yeah. Any other questions? Yeah.
Does the number of parameters include your constant like beta 0 or no?
Yes. Because like I said, if you change your model, you're not going to have the same beta 0 between models. Yeah. Yes.
And we're expecting a high value for deviance when we're dealing with a smaller number of parameters.
I'm sorry?
I mean, when we're expecting a higher value for deviance, when we are dealing with a lower order
Okay.
lambda or with higher.
So you expect more deviance with lower parameters because you like just having less numbers explain the data, you're going to get bigger errors.
Yeah, so it's like a trade-off finally.
Yeah, it's a trade-off, yeah. Yeah. Okay, cool. So I'll hand it off to Antonio, who's going to talk about Dr. Chip's material.
All right, yeah, so I'm going to talk about Dr. Chib's stuff. This is actually a typo. I was going to talk about Dr. Huang's stuff too, which is on Friday, but we don't have that yet. So for now, it's just lectures 11 and 12. Do we have a clicker? Okay, so just as a general overview of his material, what you really need to know is basically how do fMRI and BOLD work and what are the limitations of that. how you tell a good MRI study from a bad one, how to calculate an expected value. He went over this with the coin flips at some point during his lecture. In what way was the paradoxical performance study designed? And then what were the findings about loss aversion and performance? And then finally explained this reappraisal framework, which was just kind of their conclusion from the study that they did. So just as an overview of MRI, an MRI machine has a couple main components, basically 3 components. So you have essentially a really strong magnet, which is between 1.5 and 9 Teslas. And also Gauss is just a different version of Teslas. They're the same, it's just a smaller unit. So basically you have a really strong magnet, and when the patient's in there, you turn that magnet on, and all the atoms in their tissues are under this magnetic field. And then you have a gradient coil, which is a radio frequency transmitter, and a radio frequency coil, which is the radio frequency receiver. So basically, under this strong magnetic field, you ping a radio frequency at their body, and then as the atoms relax, what comes back is what you pick up on the RF receiver. So I'll go into that in a little more detail here. So the first step I was talking about, it's just a really strong magnetic field. And the nuclei in your body, this is why it's called nuclear magnetic resonance imaging, is that when you put them under the strong magnetic field, they line up along with that magnetic field where the vector is the arrows there. And most of them line up along with it. Some of them line up reverse, but most of them line up in the same direction. And that diagram in the corner is just an explanation of like the spin on atoms. It's not that important to know what spin is. That's more of a physics thing. But that's what gives them this sort of magnetic dipole. And so before you turn the magnet on, they're just all facing in random directions, but then they align really nicely. Oops, wrong way. So another thing to know is that they don't align perfectly. There's something called precession, which is basically just if you imagine the magnetic field vector as the z-axis, they align along with it, but not perfectly, so that they're kind of tilted at an angle, and they spin around that at an angle. And the angle of precession changes during excitation when you apply that RF pulse, and during relaxation when the RF pulse comes back. And that's what you actually pick up on the MRI signal. And yeah, the change in precession gives you that RF signal, which is the MRI signal. So as I was mentioning, the excitation, when you hit the body with the RF signal from the gradient coil, the tilt, that angle of precession that I showed, actually increases such that the arrow representing that precession tilts more towards the XY axis. And then so the pulse is delivered from the transmitter, they tilt more. Then you let go of that pulse, and over time, those nuclei relax back towards their original precession angle, and they release a new radio frequency signal, which you pick up with the receiver. So this is called nuclear magnetic resonance, or NMR, and just as a little bit of trivia, that was first invented in the 1950s, and there was a Nobel Prize awarded for it. It was first used for like analyzing chemicals, like in orgo, and then about 20 years later, they figured out a way to apply this medically and created the MRI machine, which was patented in 1974. So when you measure the relaxation, you measure it by 2 different times, T1 and T2. So that's the decay on the XY axis and the recovery along the Z axis. Because as you can see in this spiral over here, when it comes back to its original angle, it doesn't like come straight back, it slowly spirals around back to it. So you measure those 2 different times, and as it says there, the different types of tissue have different T1 and T2. So that's pretty much it. Slice selection, so the way you get different slices of human body is simply there are a lot of different magnets that you can turn on along the MRI machine, so there's probably a lot more slices than that, but basically you would just start at one end of the region you're looking at and turn those magnets on, get your MRI data, and then keep moving along by turning the magnets on in succession. Okay, any questions on anything so far? Pretty straightforward. So now moving into the BOLD, which is the basis for functional MRI or fMRI. BOLD stands for blood oxygen level dependent. And basically the most simple way to describe it is that when neurons have activity and are synapsing, not necessarily their firing rate, but when they're actually synapsing, they need more energy and oxygen. So they release glutamate, which is a signal that they need that extra oxygen. the body responds by increasing blood flow to that area where the activity is happening, which increases the concentration of oxygenated red blood cells and the number of them around. And then the oxygenated blood cells actually have a stronger MRI signal than the deoxygenated ones. So when you see a stronger signal on the bold fMRI, you know that there's more activity happening in that region of the brain. So basically thinking and increased neural activity is translated right to increased activity on the MRI screen. So some properties of it in general. There's a huge delay because obviously when you release this glutamate, that's a chemical thing and it takes a long time for your body to figure out that blood flow. We're talking about neural activity can change within milliseconds, but the peak bold response is about 4 or 5 entire seconds after the stimulus or after the activity starts. So it's kind of slow, so you have to kind of go back and figure out what was going on during that time period. And then the temporal and spatial resolution are kind of coarse. So the temporal resolution is in a few hundred milliseconds at a time. And the spatial resolution, the voxels, which just means a 3D pixel, are basically 1 to 3 millimeters. So when you think about that size scale of a neuron, that's huge. That's like you got hundreds of thousands of neurons in each voxel. So that kind of limits the power of fMRI because you can't track like individual or small groups of neurons. You're talking about huge chunks of the brain basically. But at the same time, it's got a huge advantage because you're basically getting a live video of what's going on in the human brain without having to make any kind of cuts. It's totally non-invasive. And the last thing, another limitation is that it's a relative measurement. So like if you see increased activity in the MRI, you can only be like, okay, when we showed them this stimulus, their activity increased in this region by 50%. You can't say like, oh, it increased by 100 spikes per second. It's only relative to whatever your control condition was. And then this is the framework of how you actually do an experiment for MRI. So you have the patient in the MRI machine and you make them do a task or you present some kind of stimulus. And then you measure the bold fMRI signal. And then your data analysis for each voxel, you do a independent statistical test. So those are some of the kinds of tests, ANOVA or like GLMs that we had talked about before. And then one really important thing is you need to have a good control condition, and you need to make sure your control condition controls for everything except the one thing that you're examining. Otherwise, there could be confounding variables going on in your experiment. And some problems with it are spatial and temporal autocorrelation. So you want to assume that each voxel is actually independent, but if you think about it, neurons are constantly communicating with each other, and the voxels have no sort of, they're just regularly spaced. So neurons between voxels are definitely affecting one another. And because of things like long-term history, short-term history, the neurons within a single voxel are also affected by what was going on before. So the time and the space are not independent of each other. And then some further limitations. So the 3 in red I think are the most important. These other ones were also mentioned, but like I had said, yeah, it's kind of coarse spatial and temporal resolution because the time bins are pretty big and also the voxels are large compared to the size of a neuron. And since it's easily misused, there's a lot of studies out there which maybe don't have good control conditions or are poorly designed, so they're putting out conclusions that are kind of dubious at best. And then it measures the synaptic activity based on the glutamate, so it doesn't measure the spiking rate of neurons. And then also the relationships between spikes and synaptic activity and your bold output are not constant. They're always changing over time, so you can't ever really get a good track on those. So finally, how do you spot a good or bad MRI study? So we keep going back to this control condition that I was talking about, which is where he says compared to what. So for example, if you were showing someone faces, your control condition can't just be like a black box or something. It has to be an image. It would have to be an image that has all of the same characteristics as a face, as far as like, I don't know, like the size, the shapes, the color and like shading values in the image, but it can't actually be a face. You have to try to control for every possible element that might affect someone's thinking, except for the very one specific thing that you're looking at. So that can be really hard to do with an MRI experiment. And then finally, he talked about this stuff called reverse inference, where basically if you say, okay, we know that X invokes process Z in the brain, and now our study is showing that Y invokes process Z. So therefore, our the observations, the activity we're viewing, which is process Y, goes back and invokes process X. Now you can do that, and that's done a lot in MRI, and if you do that properly, that's fine. But oftentimes people don't have a strong enough argument and just make a conclusion based off of that. So what the important things to do, let's see. Yeah, so other than control, so back here we have the reverse inference down there. So you need to make absolutely sure that the region you're looking at is the exact same region. And because even within a brain region, there may be many different subregions or things like that. So you have to make sure you're specifically that both processes are activating the same region of the brain. And you need to make sure that the thing that you're looking at is specific to activating that region. There may be many other things that activate that. Like in his study, he was like presenting incentives. Maybe if there was an MRI study that showed that activated one part of the brain and connected to that as something else, but there could be many other things that activate that part of the brain. So you have to be careful with that. Okay, so moving on to his second lecture. He was talking about this phenomenon called paradoxical performance, where as you increase incentives, people get better at doing a task up to a certain point. When the incentives get too high, they actually start to decrease their performance and they kind of choke under pressure. Some things that I think should be made clear about this is they're only saying it occurs for skilled tasks, and specifically they were talking about a monetary incentive. It may apply to other incentives as well, like in the soccer example he was using, but the most important thing too is that the incentive has to be large as well. To really put that pressure on, it has to be a skilled task with a large incentive. Otherwise, you probably wouldn't see this kind of parabolic shape. And then he said basically, it's not well understood. The old hypothesis the people were using was something called overmotivation. Nobody really knows what that means. There's no neural basis for it. It's kind of like a hand-wavy explanation of why this happens. So he sought out to actually find out what's actually going on in the brain when this occurs. So they looked at a specific region of the brain called the ventral striatum, or VSTR, which is known to encode gains and losses, or rewards and punishments. So it encodes kind of the value of how big the gain or loss is, and affects actually your motions and behavior. So there's a link between the VSTR and your motor cortex. And when you're actually performing a task, based on how big the gain or loss associated with the task is, it'll affect how you perform that motion. So they designed a study to find out why paradoxical performance occurs. So what they did here is they designed a completely new virtual task that a patient could do in an MRI, where they have this ball attached to a spring, and they have to drag that gray ball while the yellow one is bouncing around. So it's a really difficult task and something no one would have experience in. In that way, it'd be completely new to the subject, so you wouldn't have any confounding effects from people coming in knowing how to do it. And it's really difficult, and they also could standardize it for each subject, because some subjects are better than others, but you want them all to be at the same difficulty level. So some subjects, they standardize it so that the box would be smaller for them than other subjects, basically. And they use motion cameras in the MRI to track as they did this activity with like a pointer. So the first step of this experiment was training the subjects. So in the beginning, they were really bad. They had like 10% success rate. So they did 500 trials with everyone and got them up to about a 75% success rate. And then this is what I was talking about with the thresholding. So for each individual subject, they created a psychometric curve, and they got a threshold for easy, which was when they were 80% successful, and hard, which was when they were 60% successful, so that each person would have those individual box sizes specialized for them. That would be easy and hard. And then finally, onto the meat of the experiment, the actual incentivized task. So they present them with, they tell them, okay, you're going to win a certain amount of money if you do this right. And they did this over many trials. And then they actually they pulled a random trial out of this study, and they actually gave the person that amount of money. So it was a real incentive. And it was to their advantage to do as well as they could, because the more high value prizes they won, the more likely they were going to get one of those at the end of the study. And they generated a GLM to describe this. He showed the GLM in the slides. I don't think that exact GLM is going to be important, but it's cool to know that he actually applied the same stuff that Dr. Sarma was talking about to this experiment. And then so they would try to move the ball into the box. If they got it, they would be told that they won that amount, otherwise they lost it. So their initial results are exactly what we were talking about before with paradoxical performance. And this is what I was saying, with an unskilled task at the easy level, they just got better as the money amount increased. But with the skilled task, they got better as the money amount increased to, say, $50, but when it went to $100, they completely tanked and they did worse. So this is just showing that with a skilled task, you have that paradoxical performance curve. So now that they know that this is occurring in their study, they have the fMRI data, and they're going to try and find out what's going on within the brain when that failure, that choking under pressure is happening. So what they found here, looking at the VSTR, which we know is the region that encodes those gains and losses, this is where they debunked the overmotivation hypothesis, because they found that neural sensitivity had nothing to do with performance. So how motivated someone wasn't affecting them choking under pressure. That's not what it was. So what they did find was that actually, you see in the red regions of the brain there, that's encoding potential gains, and the blue means it's encoding potential losses. So red is activating and blue is the deactivating, meaning they're thinking of it as a loss. So basically when they were first presented the incentive, they saw it as a gain, and your brain like automatically assumes, oh, I won $100, even before you've done the task. And then as you actually go to move the ball into the box, suddenly your brain reappraises that and says, uh-oh, like if I screw this up, I'm going to lose $100. And they see it as a potential loss. And that's when people panic and choke under pressure. So just to talk a little more about the loss idea here. So expected value and loss aversion. So you guys should know the expected value formula. It's really simple. It's just the probability of a gain times that gain, plus the probability of a loss times the loss value, in which case here the loss value would be negative. So he used this example where they used this to find people's loss aversion. So they actually used this during their study to find how loss averse individual people were, which we'll come back to later. So what we find here is that most people are loss averse in general, and as it says, losses loom larger than gains. So if you're doing a gamble, the gain amount has to be a lot larger than the loss amount. So you have to have a pretty high expected value to actually want to do that gamble. Even when, say in this case, you have $22.20, your expected value would be 1. So if you do this enough times, you're going to win some money, but almost everyone would actually turn down this bet because our brains are so loss averse. Now, not everyone is loss averse. Some people are actually, not loss averse, but it's more rare. So tying this back to the MRI study, what they found was that more loss aversion led to poor performance during this ball in the box experiment. So that was kind of the root of what they were seeing. If someone was more loss averse, they would actually have more deactivation in their VSTR during that task performance, which would cause them to choke more under pressure. So the more loss averse people are freaking out more when they're actually doing the task and seeing it as a much bigger loss. And they found this out. This is like the third graph of a series of 3 that he showed in his slides. Basically, they tied loss aversion to deactivation of the VSTR and then combined those graphs to get loss aversion shows poor performance. But this is the most important one. That's the conclusion of it. So then they came up with the idea of reappraisal, which I already talked about. Basically, what they think is going on is that somebody thinks they have $100 when they see that they could win it. And then when they actually go to get it, they freak out because they think they could lose it. So what they did to prove it is they switched it from a gain frame to a loss frame. So instead of presenting the possible reward as a gain, they now present it as a possible loss. And what they think should happen is that these loss-averse people should actually succeed now. Because if they initially see the reward as a possible loss, then that gives them a few seconds to get themselves ready and sort of reappraise it to, okay, well, I've already lost it. Now I can gain it. So that's what they tested now. And so he showed 2 frameworks. He showed like this is the real framework and then the alternative one. It can get confusing, so I'm just going to show you guys this is what is really going on. So let's see, is the pointer work? Yeah. So here's what they found in the first study in the gain domain where they present it as a gain. When people have a lot of loss aversion, they choke under pressure. If they're not loss averse, they do fine when they're presented with $100. So now if they present it as a loss instead initially, the people who are loss averse actually succeed and do better. And the people who aren't loss averse actually choke under pressure. So it's completely opposite. So loss averse people, which is most people, choke when the incentive is presented as a gain and actually succeed when the incentive is presented as a loss. And that's just showing the actual data. So those are the ideal curves that they predicted, and then the actual data definitely shows that. You can see it's increasing here, and you have this paradoxical performance in the two corners.
Why is it negative from the beginning?
Negative?
From the z-score, what is it comparing to?
So it's basically like if you have a low incentive, you're not going to want to do very well. Like this amount here was like in like that's like for the $0 to $5 rewards. So people like don't.
Like, what is it? Why is the value like negative? What's it being compared to?
I guess the average performance, possibly. Like I guess they might have plotted their total performance values as like as a PDF, and then gotten the z, negative or positive if it was better than or worse than average, something like that. Yep.
What does it mean to present an incentive as a loss?
Right. So that's back here when it was literally they did this so how the experiment worked was they first flashed something on the screen where it would say you won $100, you can win $100, and then a couple seconds later the person would actually do the task, and if they got the ball in the box then they could win that amount. But instead now they flip it around and they say they actually flash on the screen you can lose $100, and then they had the person do the task instead. So does that make sense? Yeah. Yeah, and this is just showing that during the actual performance of the task, the VSTR deactivates whether or not it's a gain or loss. I don't think that's that important to know. And so finally, moving out of the VSTR, like I was talking about before, it connects to the motor cortex, which is actually what's causing the choking. So based on an incentive, your VSTR actually connects over to your motor cortex, and it has something called functional connectivity, where it's actually kind of influencing and controlling how your movements go based on the reward possibility. And when you choke under pressure, this functional connectivity actually gets weaker, and that's what's causing you to choke under pressure. So what happens in the loss domain is that a person who's loss averse is presented something that they think they can gain, and to them they feel like they've already won it, and then as they choke, the VSTR deactivates and your functional connectivity to your motor cortex is decreased, so your motions are actually sloppier and your performance decreases. And you can see that here, so this is your loss aversion level, so more loss averse over here. And this is the difference in functional connectivity, loss domain versus gain domain. So that means that for very loss averse people, they have a large difference in loss versus in how they perform when they're in a loss frame versus a gain frame. And they perform better in the loss frame, and then as they go into the...
When you say gain frame, is that which one is presented as?
Yeah. Loss frame means they present it as a loss initially, and gain frame means they present it as a gain initially. Yeah.
How do we define the level of loss aversion?
So the level of loss aversion, that's a good question. Going back to this expected value. So they did this experiment where they had coin flip gambling games, and they found how much greater a win would have to be than a loss for someone to take it. And they did this for every subject in the study. So then they found how much bigger they had to see a win than a loss. And that's how they got the loss aversion, which was, I think, the slope of this. Yeah.
What was the unskilled task that they presented the people with versus the skilled one?
So I guess in this case, they didn't have skilled versus unskilled. It was always a skilled task, but they had the easy level, the threshold where for each subject, that was how big the box was for them to get 80% of the trials right.
Is that how the data was gotten for the one that was like unskilled and it was just linear?
Right. Yeah, right here.
What?
Or let's go back.
That one.
Easy. So I guess in this case, you can see easy as sort of unskilled and hard as unskilled. Easy means the box was much bigger, so they had a lot easier time getting it into that. And then the hard was with a smaller box. Okay. And then, so that's pretty much it, just to summarize. So the VSTR and behavior respond differently when something is presented as a loss versus a gain. And they believe that reappraisal is what actually causes this paradoxical performance. The reappraisal results in a decrease in the connectivity between the VSTR and motor cortex, which is called choking under pressure. And they believe this can be applied to theories in psychology and economics to change how incentives are presented and how people work, and prepare people for high-stakes situations, basically. Any questions on that? Cool. Okay, that's everything.